Okay, let me review just real briefly what we went through what we started to do last class, which is a class called quantum correspondence for the transverse field Ising model. So we're taking a d-dimensional quantum many-body Hamiltonian, or partition function more accurately, and transforming it into a d plus one-dimensional classical Ising model. So we haven't quite finished this final step yet. So let me just mention something about the Trotter decomposition, because I was a little sloppy with my notation. I noticed last class. So when we write the partition function as what I'm calling a functional integral, but it's just a product over sums of basically sums that occur from the resolution of the identity. I was labeling them with tau, but tau isn't an integer, and this product should properly be labeled by an integer. So I'm going to introduce a label L for that. So tau is tau counts the expansion direction, or the inverse temperature direction, or the imaginary time direction, which I call it for a specific reason, which we'll see, in units of epsilon. So 0, epsilon, 2 epsilon, 3 epsilon, all the way up to beta minus epsilon. So really what tau is just L times epsilon, where I'm introducing an integer that I'll use to label these products. And L goes from 0 to m minus 1. And the L equals 0, tau equals 0 state is the trace that comes from, it's the trace that occurs in the partition function. So I can label these basis states with that label L. Okay, so that's a product of all the sums. That's just a compactified notation. Then I have L from 0 to m minus 1 products of basically these matrix elements, which I was solving last time. So let's see if I can write these. So I'm going to say this has to be L plus 1 times epsilon. That's your sigma prime. It's a matrix element of these two exponential operators, and then the basis, the many-body basis state, which is just tau L, so L times epsilon here. I think that's right. So last time I think I wrote this is tau, but now I'm labeling it with this L index, so it's just tau L. And this one here would be tau L plus epsilon. Okay, so it's that matrix element that we're trying to solve. Does that make sense? So that's after inserting all the resolutions of the identity. Okay, so we have this big expansion direction, which I'll draw graphically in a minute. The generic matrix element, so I was calling this just generically sigma prime, and that was sigma. So last time we derived something like this. And I introduced this exponential form, which had a coefficient a, and there's n of them. So that's supposed to be the exponential. And I introduced K2. And the second part is the original H one or interacting Ising part of the Hamiltonian. So here, K1 is just epsilon times J, where J was the Ising coupling of the original Hamiltonian. And I solved for K2 last time. It's just something. It's something that depends on the transverse field H. I probably solved for A too at some point. Yeah. Okay, so let me write that matrix element slightly different. As just I just wrote the sum as a product out front of the exponential. Actually, I'm not sure which one I like. Well, the product tells you that basically you have this extra expansion direction, but let me write it more like a 2D lattice model. So the full partition, that's just a matrix element, right? So the full partition function, Z, carries around all this bulky preamble. Before the matrix element. So the matrix element will be yeah, I like it like this. Okay, that's K2 plus K1. And this will be sigma I tau L, sigma J tau L. That's it. Okay, so. And there's probably a coefficient out front that has to do with all those A's. Okay, so there'll be some sort of A, M. Yeah, I've pulled out end products of that, so A and M out front. Which is just some constant. It doesn't contribute to the sort of overall stat mech of the problem. So if you look back at the partition function that we wrote, well, if you look back at any partition function that you've written for a classical system, that's basically all this is. But it's just written in a funny way, where here I have sigma variables. You know, your degrees of freedom are these sigmas, right? That's the spins. That's a Pauling spins. But they're all diagonal now. Okay, so the Hamiltonian, which is this thing, now commutes with the sigma. So it's completely classical at the cost of, you know, the interacting term occurs in the original sort of space-like configurations. Remember, this is nearest neighbors. Nearest spatial neighbors. And these are the same tau slices. Or the same occurrences of tau, whereas these occur on the same site. But different tau. So the partition function, if I wanted to draw it sort of graphically, imagine that I just have a spatial dimension. And a inverse temperature or expansion or imaginary time. So the spatial dimension is just labeled by these I and J's. Okay, so I can imagine having lattice sites. It would be a hypercube if I could draw it, but I'll just draw it as a one-dimensional lattice. This could be site I, this could be site J, for example. Nearest neighbors on a one-dimensional lattice. And then in this direction I have tau, which starts at 0, epsilon, 2 epsilon, all the way up to beta, which is m times epsilon. Beta is m times epsilon. So there's m integer imaginary time slices is what I'm calling them. Okay, well, it's a crummy lattice, but all this is a two-dimensional lattice. The interaction K1 occurs between nearest neighbor sites, and the interaction K2 occurs between same sites but different times. That's supposed to be K2, the green. Okay, so it's just anisotropic. So that's the price you pay somehow. You've taken the isotropic, uniform. There's only one K for every single interacting bond. And you've expanded things out into an extra dimension and made it highly anisotropic. That's sort of the simple picture of what a quantum field theory looks like. And we've just done it in a very concrete way. So there's a couple things to note. The first thing to note is that you've taken a fairly simple looking Hamiltonian and made it very complicated, right? And so this anisotropy is sort of the price that you pay. It's this like complicated Hamiltonian. So you have to believe, or you have to convince yourself that you haven't changed the physics of the problem with this anisotropy. That's generally not a completely trivial statement. So in general, these couplings have a relationship to each other, K1 and K2. There's a critical point in the 2D. As you know, there's a phase transition in the 2D classical Ising model, right? And as you're looking at on assignment 1, question 2, there's a quantum critical point in the one-dimensional transverse field Ising model. Okay, so you could ask yourself if the physics of this phase transition or this critical point in one-dimensional quantum and two-dimensional classical is the same. And it is the same, although I'm not going to convince you of that in this class. That's something for, you know, Phys 705. So when you study universality and so on, you'll see, I guess, in a more deep way why there's this relationship between classical and quantum physics in that case. But in some very deep sense, the transition from ferromagnet to paramagnet in the 2D classical Ising model is the same as the D plus one-dimensional, or so the two-dimensional classical model and the one-dimensional quantum model. And in fact, the theory of that critical point, you know, the low energy, long wavelength theory of that phase transition in both the quantum model and the higher dimensional classical model is essentially exactly the same theory, and that's what's the subject of 705. Okay? But for us, all we want to do is sort of, I guess, be motivated that field theories or quantum, you know, Hamiltonians have this D plus one-dimensional structure. Okay? And one can always, you know, even if the exact theories of quantum and classical aren't the same, one can always reformulate the quantum theory as a higher dimensional classical theory, even if you have to retain all this complicated coupling and so on. And in fact, I could take this highly anisotropic model in D plus one dimensions. Since it's all classical, I can just put it on a classical computer and solve exactly the phase diagram of the one-dimensional quantum model. And that's basically the strategy that quantum Monte Carlo takes. So it should leave you asking, what is quantum mechanics then, if any many-body quantum system can be described as a one higher dimensional classical system? And so that's a subtle question, I think. We'll see what it means in the field theory language to actually be quantum mechanical as this course goes on. But it's not just, you know, it's not as straightforward as just saying, oh, you have operators that don't commute, blah blah blah, right? Because I can essentially determine any equilibrium stat-mech property of that quantum model using just a simple classical description. Okay? That's the basic idea of quantum to classical correspondence. We're going to start formally deriving basically field theory representations using a Feynman path integral approach. But before I do that, I just want to take a sort of detour into second quantization. So any questions on this derivation or lack of derivation that I gave in the last couple classes? This is the picture I want you to keep in mind basically when we move on to bosons and fermions and coherent states and so on. And again, the basic idea is that you've inserted a whole bunch of resolutions of the identity, m-1 resolutions of the identity, and solved the matrix element. Okay? And that solving that matrix element eliminates the quantum operators, because you write those matrix elements as scalars. Cool? Who's heard of second quantization? Most people have. So I'm just going to review it for the rest of this class. Just so you get the basic notation that we're going to use as we move on. And in fact, we're already using second quantization in that Jordan Wigner problem in your assignment. You see the C dagger operators. Okay, so let's just get our sort of notation, our motivation and our notation straight for second quantization. And we won't mention it again after this class. And second quantization's handled well in many books. So I'm mostly going to sketch out motivations and write down all the relationships without explicit proofs. So I'd refer you maybe to Altman and Simons. Maybe. I don't know how to spell that. Altman. I think it's called Condensed Matter Field Theory or something like that, that book. There's a whole chapter on second quantization. Most books on sort of quantum many-body theory start out with second quantization. We've been talking about SU2 invariant spins, right? We've been talking about Heisenberg and Ising models and XY models and blah, 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 spin 1/2 systems. But I want you to start thinking about bosons and fermions. And you can imagine an itinerant system of bosons and fermions, or fermions. So a system where you have particles that maybe aren't on a lattice. They might be moving around in the continuum, or they still could be on a lattice. You could have a lattice model of bosons or fermions, like the Hubbard model. But they're identical because it's quantum mechanics, which means they're indistinguishable. And so the way that we're used to writing a wave function, okay, for such particles, for example, in position space, I would take my wave function. So when you draw it as a ket, it's just a general, just some abstract object that hasn't been represented in any basis yet. And if I put it in the position basis, so it's a many particle system, I might write my wave function like this. Or in shorthand notation, just a wave function that involves the set of all positions of all particles, if you will. Now, if your particles are indistinguishable, if you exchange the labels on any two particles, then something shouldn't change, and that something's your probability density. So as in quantum mechanics. So the probability density is just psi squared. So I'm going to call it particle labels. So if I switch 2 and 3, it's the probability density, this thing, that should be unchanged. So that switching of the labels is called a permutation. Okay, so if I apply that permutation, or exchange if you want to call it that, so to two labels, J and K, I was defining that operator as the thing that takes particle J and switches its label with particle K. In order for the probability density to remain the same, then this is only true up to a phase factor, e to the I phi. Right? Because when you take the norm square, that phase factor drops out. But also, if you apply the same permutation operator again to this state, so you exchange J back with K, you should really get the same wave function back. You shouldn't be left over with a phase, right? So that means that this phi is restricted to two values, 0 or pi, right? Because it's a second exchange is 2 phi. So that's a simple sort of hand-wavy argument for the existence of bosonic and fermionic statistics. One of these options gives you bosons, and the other option gives you fermions. This is even under permutation. And this is odd under permutation. And that's it, right? Is there any other possibility under God's green earth for particle statistics that you know of? No? You ever hear about anions?
How do we account for the path that, how we switch?
We'll get to that. Yeah. In second quantization, that's important. So before I get to that, if you're working on topological quantum computing, you should learn what an anion is, but I won't teach it to you. An anion means that you have a particle where another option besides 0 and pi exists. Okay, and that's a special case that only applies in 1 dimensions or 2 dimensions. It seems sophisticated, but it just means like any other phase besides 0 and pi. So I don't know who named it, but it's an anion. There's many different types of anions. And they happen when you have a basically restricted spatial dimension, and your permutations aren't the only essentially sort of symmetry of the wave function. So these are related to the so-called braid group. So it's a braid group and not the permutation group. And the braiding of anions is essentially the model under which universal topological quantum computation lies. So these are important for. So look up Ising anions or Fibonacci anions. So think Fibonacci anions basically are made up of are a consequence of a braid group that gives you all the universal gates needed for a universal quantum computer. And so, people trying to build a topological quantum computer not only have to build the stable topological quantum bit, they also have to produce the gate operations which correspond to the braid group for anions. So that's something above and beyond basically just storing a topological quantum state. So we won't talk too much more about anions in this class, although I will talk a little bit more about gauge theories, Z2 gauge theories. Back to bosons and fermions, as you know, the spin of the boson and the fermion is related to the statistics, or related to this phase factor. And that's called the spin statistics theorem. So as you know, for spin, I don't know, integer, any integer spin particles of boson, any half integers of fermion. And that's not immediately apparent from anything I've said. But that's the spin statistics theorem, which is basically an axiom of quantum field theory. Okay, so the proof requires something a lot more than we'll develop in this class. You could take it as an experimental fact if you want. But anytime you have a spin, anytime you have a particle made up, even a particle made up of a composite composed of many bosons, say you'll get a boson. And if you have a particle composed of an even number of fermions, as long as you're at an energy much lower than the binding energy, then for an even number of fermions clumped together, you'll get bosons, and so on. Okay, so the statistics of the many particle system is integrally tied to the spin of the object. But so now, what about second quantization? So what am I getting at? So first off, remember how we generalize a wave function, a single particle wave function, to the n particle case. So we want to account for what I'm going to call symmetry and antisymmetry. Right? So even symmetric, odd is antisymmetric under this permutation operation. We want to account for this in the wave function. Well, we can start by defining a single particle state, which I'll call phi, a different phi than that phase. And in an n-particle Hilbert space, I could write the wave function as just a tensor product, I guess. Okay, so this is all the single particle states, tensor product, if you will. Maybe I'll call it something like this. But you have to be careful about the symmetry when you write that tensor product. So it's not quite as simple as that. So if you're dealing with bosons or fermions, what you really want is all that permutation symmetry accounted for. And so the symmetrized tensor product, or anti-symmetrized, would be let me write it explicitly as a many-body Hamiltonian, or many-body wave function. Okay, there's some combinatorial factor, and then there's a sum over all possible permutations, which I'll explain, plus a phase factor. And I have to use this single particle label, but I have to be able to permute all the single particle labels, like I was talking about here. And so I'm going to label these with P's for the permutations. So permutation N, R, N. Okay, yes. Okay, so this sum runs over So the sum runs over all permutations of the state labels. Okay, so one element of the sum is 1, 2, 3, 4, 5 up to n. Then I permute 1 and 2. So the second element of the sum might be 2, 1, 3, 4, 5, blah, 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 right?
What's the row there?
And the row is what tells you whether or not you have even or odd symmetry under the permutations. Okay, so I'll say rho is the sign of the permutation. It is +1 for bosons and -1 for fermions. So it's +1. So it's +1 if the number of permutations required to get back to the original form is even, and it's -1 if that's odd. Okay, so Okay, so it's turns out to be 1 for bosons, -1 for fermions. So I'm not exactly proving everything, like I said. I'm just running through the basic arguments. So if anything looks really foreign to you, definitely look at Altland and Simons. But you can basically understand that this is a symmetrized tensor product when you start to write down some examples. So if you look at an example for bosons, this is just the general way of writing the n particle state, but let's look at some specific examples. So for bosons, I'm even under permutation of particles. So let's look at a 2-particle state. So for example, okay, so I have psi. I'm going to label it with my 2 single particle states. I just call them L and K. And there's 2 position labels. Okay, so I need a 1 over root number of particles. And then I need a sum over all possible permutations. L and K, R1, R2. So it'll be K, L, R1, R2. So it's exactly what you expect for bosons. For fermions, that minus sign comes into effect, of course. Okay, so for 2 fermions, I can write this wave function. Same normalization, 1 over root n, factorial. Now what do I want? I want L, R1, K, R2, minus K, R1, L, R2. Because the row in front of the second term, right, is -1 because it takes an odd number, which is 1, permutations to bring this back into its original form. Okay, and so for bosons, this thing is just, so LK is the same as KL. And for fermions, we get minus KL. That's what we required under the permutation operation. Simple as that. You might have seen this wave function written in a different way for fermions, for the n-body fermions. And that's the Slater determinant. So for many electrons, then we get the Slater determinant. So I'm going to write the particle label instead of just having 2 particles. I have a set of particles, n particles. Okay. And I also have a set of position vectors. Okay, so that's a general n-body wave function. And another way to write this is with the determinant for fermions. Okay, and the J labels, okay, count up as I count columns, and the I labels don't. They count up as I count rows. So you just take the determinant of this object, R1, J1 here, R2, J2, R2, what, J and R2, down to J1 Rn, and okay, so if you put n is equal to 2, and you write out that 2-electron state, you'll get that antisymmetric wave function there.
Isn't the sign of the permutation the same in those cases?
It requires 0 permutations to return to the original labeling here.
Well, the KL. Okay. You mean the full, like the permuting, the full wave function, not just a permutation?
The number of 2-element transitions bring P back to its original form is even or odd.
Bring the full wave function back to its original form?
Yes, oh yeah.
Okay.
So all the labels in the wave function, to bring it back to its original form. Yeah, so it's basically, it's like if you permute this once to get the wave function back into its original form or not,
Okay.
versus 0, just a mod 2 argument.
So it's not to bring back an individual permutation to the
Yeah.
original permutation, to bring the full wave function to its original.
Because P is a label. Okay, so say you have a label. Well, okay, so if you have this label here, right, and you want to bring it back to its original form. Yeah, the coefficient's always 1 anyway for bosons, so it only matters for fermions, right? But it's to bring the full wave function back to its original form, I guess, because no, that's an element inside the sum, right? So if you want to bring this element of the sum back to its original form, that's yeah, that's what it is. Sorry, that's this minus sign.
Okay.
Yeah,
And then for the other one,
it's always 1.
okay, so
Yeah.
it doesn't depend on the sign of the permutations for bosons.
Yeah, it doesn't matter. It's always 1. Yeah, I'll write it in a different way. It should be rho to some power. That's the sum overall. So, okay, I'll fix it. But yeah, so this is that row here, right? Sorry. I don't know. Maybe you like the Slater determinant better, because then you don't have to like figure out what that row is. So the nice thing you can see, it's the same thing, and you see that if you have 2 labels that are the same for fermions, the wave function vanishes and so on. So if T labels are the same, which means 2 particles are in the same single particle state, right? And that's just a statement of the Pauli exclusion principle. that was basically a review of first quantization. Right? So a first quantized wave function for an n-body system is just written in one of these ways. You know. So the problem with the n-body wave function in first quantization, I guess there's sort of two problems with it. I mean, first of all, as you just figured out, these expressions suck. You have to figure out how all these permutations and stuff basically work for fermions. And I think this is the best way to look at it. But you have to calculate this determinant every time. And like, who wants to do that, right? So as bad as this is, if you have an expectation value of a two-body operator, they get worse. So imagine an expectation value of some operator. So you have a first quantized wave function, which means you have to integrate over all spatial positions of all the particles. So you have 3 times n particle integrations because you're in a 3-dimensional space here. Then you have the wave function, the many-body wave function, which I'll just write like this. So it's conjugate, you have the operator, you have the other wave function. All right, I probably made mistakes just writing it. So this involves something like, 3 to the n integrations. So 3n integrations. This, these 2 wave functions, as you can see above, each one of them has n factorial terms in this permutation. So you have like this number squared elements in this product. And never mind the operator itself could be an n-term operator or higher. It could be 2 to the n, right? If it's like a 2-dimensional lattice, say, operator or something like that. So basically what we're doing in first quantization is we're carrying around too much information when we carry around this position label. And the other problem with this first quantization is that if we're dealing with stat mech problems, then we might want to deal with a grand canonical ensemble, which is really what you're doing in like assignment 1 question 2. You're applying in creation and annihilation operators to a vacuum, and so particle numbers are fluctuating in and out of existence, but this n is fixed in first quantization. So it's like you have many different, you have many different Slater determinants depending on which particle occupation or how many particles you have in your system. So this first quantization doesn't really deal with that well. Okay, so we're working in the grand canonical ensemble. And the grand canonical ensemble is important for these types of problems that we're going to deal with in this class where we have quasi-particles and excitations. So you should really start to think about many-body problems as is particles being excited in and out of vacuum states.
Are those phi L's and phi K's the same, or they're different wave functions?
They're different single particle states. So I could label them 1 and 2, but I just didn't want to because it confuses with the particle label.
So you have two particles which can be in two different places, and depending on where they are spatially, their wave function is going to be different.
Yeah. So there's a state. Yeah. There's two different states. So
this wave function is associated to the space, and then you either put a particle in there from some.
Yeah. So you're basically labeling a particle by its position, say. But if you look at this position and this position, there's two particles. You look at a later time, you don't know if they've been exchanged or not because they're indistinguishable.
They're the same, like spatially located.
Yeah. Yeah. So they can be they can be in different spatial positions, and they can have different states. So you think of it like if you think of the Pauli exclusion principle, you can't have two particles in the same single particle state. And so, I mean, that's one way to sort these labels out. So if you have two different particles, of which you've labeled somehow, and you try to put them in the same single particle state, you have to have 0 for that wave function.
Even if they're in different locations.
Well, the state label is like, no, I mean, the location is just like the particle label in this case. So
yeah, the location is the state.
So and if you have a bosonic system, you can pile all the particles in the same wave function. That's like a superfluid or a BEC, right? So you can have a spatially macroscopic object that's all in the single particle ground state, and that's what a Bose-Einstein condensate is. Yeah. What am I saying here? Okay. So by the way, I wrote the wave function in the position basis, like right. Where did I do it? Maybe I got it right. But I wrote the general wave function in the position basis. It doesn't have to be a position basis in order for this all to apply. Okay, so basically forget position space. We're carrying around all this extra baggage. We don't need to even think about the positions of the particles. So instead of thinking about the positions of particles and what states those particles are in, we're going to think about all possible states of the system, and we're going to just concern ourselves with how many particles are in those states. And that's the occupation number representation. Which leads to so-called Fock space, which is like an extended Hilbert space. So if I imagine that, like on your assignment 1, I have creation and I have processes which create and annihilate particles in and out of a vacuum, okay? Which means I'm creating electrons, say, or destroying electrons. Then I have many of these wave functions, which are possible. So I could have You have a variable number of particles. For example, I could have 0. And in condensed matter, that's the ground state of the system. So in high energy field theory, you're used to thinking of like a true vacuum state, or Dirac sea maybe. And you might excite electrons or holes in the Dirac sea. For condensed matter, the Dirac sea is the 0 temperature ground state of the material, or whatever it is you're looking at, the many-body system. And what we're doing, the philosophy that we're taking in condensed matter is that we're exciting quasi-particles, which are just collective excitations, in and out of the vacuum. Okay, so if I'm dealing with fermions still, so for example, no fermions, I can have a state labeled J. So I'm throwing away the particle position label. So this would just be, my state labels are the subscripts. J, some particle. There's only one particle. And I can have a state label for both J and K for the antisymmetric wave function that I wrote down there. Okay, so this is the one that I wrote down there, 1 over root 2. And so on. So if I use this type of notation, I've gotten rid of the position label, but I really want to combine these all into one type of notation where all I care about is how many particles occupy the states, right? So there's only one particle in the system here occupying state J. Here I have 2 particles occupying one particle occupying each state. So let's just write in the ket how many particles occupy each one of those states. Okay, so I use n for that occupation number, and I have all these different states, j, k, whatever they are, and I'm going to basically order them such that the sum of all the occupations is equal to the total number of particles in the system. Okay, and especially, 0 is still the vacuum state. Where there's no particles in any of the states. These occupation numbers have to obey the boson or fermion properties, in particular that Pauli exclusion principle, where you can't have 2 particles in the same state. So you can only have 0 or 1. But for bosons, you have 0, 1, 2, up to you know, the local Hilbert space is infinite for bosons. And second quantization. So this is the occupation basis, the occupation number basis. And the space spanned by all these occupation numbers, the space spanned by this basis is Fock space. And for an n-particle system, you know, there's a Hilbert space essentially associated with those n particles, depending what your local Hilbert space is and how many particles you have. And the direct sum of all of those possible Hilbert spaces is Fock space. Okay. I don't know, it's like a curly F they use. I don't know, goes up to infinity. So this is the vacuum state. This is the sort of Hilbert space of the vacuum. And that's an element of Fock space. So it's a little strange. But we need it so that we can move around within this space with creation and annihilation operators. This is like the n equals 1, you know, single particle, I guess, local Hilbert space. This is the n particle Hilbert space, if you will. And then the number of particles is undetermined. So in the grand canonical ensemble, you take the direct sum all the way up to infinity. So I've just introduced this state space, if you will, for the occupation number representation. And now you have to worry about how you produce the proper symmetrized or anti-symmetrized wave functions that are the analogy of these first quantized wave functions in this second quantized state space.
So why is this second quantized?
Why is it called second quantization?
You're calling the Fock space basis like the second quantization?
Yeah, so now we're going to represent operators and so on, and that's second quantized operators. I don't know why it's called that.
Okay, so okay.
It's just called second quantization. Anybody know why? Why is it called first quantization? I don't know. Sounds right to me. I don't know.
So
I assume so, yeah. So
is there such thing for incondensed matter systems as like coherent states? Or?
yeah, we're going to deal with coherent states in second quantized
So
systems.
Physically, what would that represent?
Well, so
Phonons would have? Like you would have?
yeah, so a phonon will be, so if you have a lattice that is cooled to 0 temperature, that's your vacuum state. And then a lattice vibration, like a single quantized lattice vibration, is a single, you know, you have to create the single one particle state, say out of the vacuum. And there's a creation operator associated with that. And it turns out in that case, the creation operators are bosonic. So that's what we're getting to now. So just because now we just have the space, right? And so if I had a single phonon in a lattice, you know, I would have, and that phonon could have different say frequencies or different energies, right? I would have these labels would be my energy labels, and I would have one particle in one of those energy labels. So if it's the first excited, like the lowest energy state for that phonon, I would put it here. But then if I gave it a bit more energy, I would put it here. And if it gave it more energy, I would put it here. And if I had two phonons, one could be in this state, One could be in this state, you know. One could be in this state, one could be in this state.
But that's, so you'd have discrete frequencies, like your photons are
Yeah.
the frequencies they can have.
Yeah, because it's quantum mechanics, so everything's discrete, yeah. So that's one way of thinking about it. You have all these different discrete states, and that's what those labels cover, right, is the single particle states, right? So if you have a single phonon excited in a crystal, but if you have many phonons, you know, if you have n phonons, then you distribute them amongst all those states, right, in different ways. That's basically what second quantization is. So that's the space you live in, and you can create and annihilate phonons, right? You can maybe warm it up or cool it down, or maybe the number fluctuates. And that's why your Fock space has to be big enough to hold all of these options.
Is there a difference between the state number and the number of particle in the states?
Yeah.
Okay.
The state number is the number 1, 2, 3, or whatever, and the number of particles in the state is that n. So if I have 3 particles in state 3, I would have something like this.
And how would you write the wave function format?
Well, if I have 3 particles in state 3, it has to be bosonic,
Yeah.
right? Because I can't have the same labels. So I could label these K's or these labels here. So I could have 1, 2,
Okay.
right, for an electron.
And then you need
So imagine you might have a ground state and a first excited state. And if I have 2 particles, if I have 2 electrons, they can't both occupy the same state. So this would go to 0. But if I had a plus here and there's a boson, then I just write the wave function with 0, 1, 1, 0. You know. So it's easy sort of for few particle systems.
So you don't have to keep track of that in your second quantization.
So in second quantization, you're just keeping track of the number in each state. Because all this is telling you, like all this thing is telling you, or that stupid permutation thing is just telling you that your bosons are fermions, basically. So we're going to take that bosonic fermion nature and just put it into the commutation relations of the operators in second quantization. Right. So that's what we have to still do.
Yeah, so my question is, if you have these 2 properties to keep track of, the state and the number of particles in that state, would you need 2 labels for your single particle wave function? That's what I'm asking.
So
the position, the number of particles, and the state number.
yeah.
Okay.
Yeah, you need the number of particles in each state.
Okay.
So there's a whole bunch of discrete states, and you imagine the number of particles in each state.
You basically need another label on that 5 there for the state number. If J here,
On this phi here, you mean?
Yeah.
These are the state labels here.
Yeah.
And the number of particles is how many particles is, like this is 0 particle, this is 1 particle, this is 2 particle. And this part here, this thing is just telling you that it's a fermion. All this nonsense is just telling you it's a fermion.
I thought J was the number of particles.
Here n is the number of particles.
Okay, so these 2 notations are not equivalent.
Yeah, more generally. So this is a different notation, yeah.
Okay.
Actually, I don't know if it's more general, but maybe it's less general. More efficiently, I don't want to, yeah, this label here is like the n. This is n equals 0, n equals 1, n equals 2.
Okay. So
That's why this notation's that's why we don't use it, basically, because
Right.
it's too bulky.
How would you write the equivalent notation for that one?
So this would be,
The matrix, I guess.
well, so this would be, yeah, 0 would be the vacuum state. This would be 1 particle in some state J, and this would be 1 particle in 1 state J, and 1 particle in 1 state K, like that. And everything else is 0.
And this one would be basically that notation.
That's this notation here. That's second quantized
Yeah,
notation.
To write this with the phi's would be this notation. You need the
This-
2 labels on the phi, which is the J1, the J2, and the...
You need, yeah, so each one of these J's is the state label. Yeah. So you have, so you have all these different state labels, yeah. I think we'll do some examples and you'll get a much better handle on it. Because we still haven't talked about how we produce these states. I'll run out of time today, so we can finish it next time. But in order to produce the states, you need properly symmetrized operators which fluctuate the number essentially, all of these different numbers, you know. And that's done with creation and annihilation operators. And I want you to think of simple harmonic oscillator when we talk about creation and annihilation operators. Okay, so we're going to introduce a set of operators in this occupation number basis. Okay, so the first one is the creation operator. So let's call it A dagger J. So I'll label all those n's. So A dagger is an operator that raises the occupation of nj, whatever that number is, by 1. Okay, I'm just going to write down the normalized, since this is taking longer than I thought. I'm just going to write down this properly normalized operator. So it's I think this notation is better here. And then n1, so it'll be nj plus 1. Okay, so I have all these states. All of these states in this occupation number basis. And I've applied an operator, which I want you to think of as like the creation operator for simple harmonic oscillator. And there's a normalization out front here that I'm not proving, but it's the same as for the SHO. It's the number, square root of the number plus 1, nj plus 1. Okay. And this rho is also, okay, so maybe I'll have you prove the normalization on an assignment. Rho is 1 for bosons. And you can't really escape the fact that you need to know. It's like when you create an operator. When you use a creation operator to raise the number of particles in a state, you have to permute that through the whole state to get it to the right position. And so without proof, that gives you this rho to the nu factor, where nu is just the sum of occupancies before J. So for fermions, all these occupations are only defined modulo 2, remember, right? So you can only have 0 or 1 in any one of these states for fermions. So that's an additional constraint on this creation operator. Who's seen this before? Right. So about half of you, okay. So again, I'm writing things down that are in all the textbooks. So if you haven't seen this, I'd actually recommend going through this a little more carefully and sort of proving this normalization, for example. So these types of creation operators, only one non-zero matrix element. Which makes everything easy. Okay, so that's the non-zero matrix element. And there's commutation. These operators have to satisfy the boson or fermion commutation relations. Okay, so from this, you can verify so IJ, JI. So if you apply this to a state, so which means if I define a commutator and an anti-commutator, for two operators with a subscript 1 for bosons, -1 for fermions. So AB minus rho BA. Then commutator and anti-commutator. Look like that. So I'm combining notation for bosons and fermions, which is a little bit confusing. If you did it separately, if you did this just for bosons, you just leave out this row and you do everything I'm doing. And then you'd have to treat fermions a little more carefully. But then fermions are easier in some sense because the occupations are just 0 or 1. They're all defined modulo 2. So I'm making maybe a concise notation at the expense of understanding anything. That's fine. Let me just write down the annihilation operator. Okay, so if I have a second quantized or an occupation basis state, and I have the Hermitian conjugate of that operator, which is just A, then the properly normalized matrix element comes from this. And then that row comes from commuting fermions. And the most important thing with the annihilation operator is to remember that if you have a state with no particles and you try to annihilate that, the wave function goes to 0. So if you operate by A on the vacuum, which is just 0, 0, 0, 0, 0, you get 0, which is different than this. It's 0. This is this is the vacuum state. And if you apply the lowering operator, or the annihilation operator, you kill that state, right? Also, I think I said this before, if you try to raise, you know, a fermionic state, which has one particle in it, you kill that state. So this is true for both bosons and fermions, but if you try to raise a state with one fermion in it, you'll kill that state too. So that's kind of that's what makes all the second quantization stuff work, is that you can simply write things in terms of creation and annihilation operators, and then basically normalize everything by doing an operation like this. Okay, so let me just write this state here. In terms of creation operators, out of the vacuum, so N1, N2, okay, this occupation number basis state is just quite generally square root all the normalization operating on the vacuum state. So these all have to be creation operators, sorry. So any general second quantized state, if you want to call it that, is written as, you know, the product of a whole bunch of creation operators applied to the vacuum properly normalized. So the only other thing I want to say about second quantization is just a little bit about how second quantized operators look. So I'll just take 10 minutes and do that at the start of the next class. But if this is completely foreign to you, look it up in books, because we're just going to start using it now. Okay. So that's basically what I wanted to waste today's class on. So next time I'll just say a little bit about these operators, and then I'm going to go right into the path integral. So I'm going to do the single particle path integral, which is like sort of the continuum analytic single particle equivalent of that d+1 dimensional classical to quantum correspondence. Okay, and that'll be the basis for how we start the many-body field theory. We'll introduce the coherent states for bosons and fermions, and then extend that single particle path integral into like a many-body coherent state path integral. And we'll use second quantization for that. Okay, so make sure you're all up to speed on this, and this all makes sense before we move on. And I'll see you guys Tuesday.